So we're going to discuss the shapes of different molecules and how do you determine the shape of the molecule.
Okay.
Now, when you talk about shapes of molecules, there's a theory which is called the valence shell electron pair repulsion theory, or VSEPR. Okay,
Okay.
that's the short. Valence shell electron pair repulsion theory. Now, what it simply states is that if you have a molecule, like if you have a molecule of BeF2,
Yeah.
that electrons in the outermost shell, they're going to repel each other, which means the electrons over here and the electrons on the other side, and they're going to repel each other. They're going to produce a force of repulsion that would keep them as far away from each other as possible, because electrons repel other electrons, right?
Yeah.
So you're not going to see a molecule of BeF2 appear to be like this, okay? Because the bonds are too close, and they're going to get repelled away from each other, okay? So is the idea clear?
Yeah.
अच्छा उसके बाद the next thing is now we're going to determine the shape of molecules based on this. The first one is number one, or you can simply if there are two electron densities. Okay, that's the first one.
Yeah.
What do I mean by two electron densities? If a molecule has two electron densities, that simply means like if you look at I mean that's BF2 molecule. So it only has two places where there are electrons. One is on the right and the other one is on the left, right? So that's electron density.
Yeah.
And the shape of the molecule is going to be linear. Linear means that it's going to be straight and the angle would be 180 degrees between the bonds.
Okay.
And there are other examples, for example, carbon dioxide molecule. Remember that consider double bonds as a single entity because the electrons over here they're together, so that's one electron density, and the electrons over here they're together, so that's another electron density. So they're going to repel each other, and the angle would be the same. So
Yeah.
always think of double bonds as a single entity. The next one is an HCN molecule.
Yeah.
Okay, that's another example. So there's a bond over here and there's a triple bond. Think of the triple bond as one thing. And they're going to be as far away from each other as possible. So the shape is going to be linear and the angle would be 180 degrees. Okay, so is this clear?
Yeah.
So now I'm going to add a few things over here, which is that, but I'm going to add that later. First, let's move to three electron densities. So if a molecule has three electron densities, how would it look like? So one example is AlCl3. It's going to exactly look like a fan. All the three
Okay.
all the three bonds would be as far away from each other as possible, so the angles are going to be, and that's the first version of this. So the angle would be, and let me write that down. This is the first version. Three bonds, or three, let's write three bonds. So the shape is going to be called trigonal planar.
Yeah.
and all the angles are going to be 120 degrees, okay, like a fan. And
Okay.
there are going to be other examples. For example, there's an SO3 molecule, so it has double bonds, but think of double bonds as a single thing. So that's another molecule. One second. This is an SO3 molecule. Okay, is this clear?
Yeah.
Then there's going to be another version of this, and that's going to be one lone pair. That's going to be one lone pair and two bonds.
Okay.
Now, the first thing is, what is a lone pair, and how do you figure out an atom has lone pairs around it? Okay, that's an issue. A lone pair is the unused. These are the unused outer electrons or orbitals.
Okay.
So completely full outer orbitals. So one example is an SO2 molecule. If you look at an SO2 molecule, it's going to be fan shaped, except on the third side, instead of having a bond or electrons over there, there's a lone pair. There's an orbital that's, I mean, the shape is exactly the same with the pairs of electrons, double bond electrons over here, double bond electrons over here. But on the other side, there's a completely full orbital with lone pairs. How did we figure out that there was going to be a lone pair? Because sulfur is in group 6. Group 6 means it has 6 outer electrons. Two of them got shared over here. Two of them got shared with the other oxygen atom. So there are two left. Okay, Amal, is this clear?
Yeah.
I said now these lone pairs are going to behave exactly like bond pairs. I mean, they're going to create a repulsion as well because they're on the outside. So the molecule is going to look exactly like a fan, except that the fan has one. You can think of a fan having one blade missing. So the shape of this molecule would actually be called bent. I mean, it's like this and this. Okay, so there's nothing. So think of a fan with one broken fan blade. Okay, you get this shape?
Yeah.
So this is an SO2 molecule, and its shape is going to be called bent. And the angle would be less than 120, somewhere between 117 and 119 degrees. That's the reason why it's going to be slightly less than 117 is that lone pairs exert a much greater amount of repulsion.
Yeah.
Okay, lone pairs exert more repulsion. Why do they exert more repulsion? Because the lone pairs are very close to the atom. The electrons, the bonded electrons, they're getting stretched by the other atom. So they're much further away. So they don't exert a lot of repulsion. So whenever you have bonds,
Yeah.
they don't they're not the electrons are getting stretched. Okay, like the way that we one second.
Yeah.
I said sorry, this is no. So yeah, fine. Amal, is this clear? Why do lone pairs exert greater repulsion?
Okay.
I said the next part. Can you try and do this question, just a small question that trying to figure out how many lone pairs a molecule has. Look at a water molecule. Can you tell me how many lone pairs would oxygen have?
Um,
Like, how would you figure this out?
would there be one, four lone pairs, right? Because isn't oxygen is in group six and it's already
Yeah.
making two more bonds.
The lone pairs are going to be two. I mean, what you're basically saying is that it's going to have four electrons, right?
Yeah, that's what I meant.
Okay. What about PCl3? P is in group 5.
Um, we would have had just one lone pair.
Okay, it's going to have one lone pair or two electrons, basically. Okay, so this is about, I mean, you must know how to find the lone pairs. So just remember, if you have three bonds, that's fan shaped. If you have three electron entities, but one of them is a lone pair, so that side is not counted in the shape because there is no atom over there. Okay, the electron's there, but there's no atom attached to it. So it's like a fan with one blade missing. So it's going to be called a
Yeah.
blade, and the angle would be almost 120 because the lone pairs exert a greater repulsion. So these two bonds would be pushed closer to each other. I said the next one is if you have four electron entities. So what's going to be the shape when you have four electron entities? And there would be different versions of this. The first one is if you have four bonds. Now, if you have four bonds,
Yeah.
the shape is going to be called tetrahedral and the angle would be 109.5 degrees. Anyways, it's going to look like this. That there's going to be a CH4 molecule. There would be four bonds. There would be one bond on the right, one coming towards you. Then you would have a bond that would be dotted that's going into the page, and there's going to be one bond that would be sitting on top. So there would be four hydrogens.
Okay.
So it's like a pyramid with one hydrogen sitting on top of the pyramid. Okay? And this shape, the good thing about this shape is that no matter how you rotate this, it looks exactly the same. Okay? It's always going to come out to be, I mean, imagine looking at it from the side. So this would be the pyramid, and this H would be sitting on top of it. Okay? So it's a three-sided pyramid
Yeah.
with a hydrogen sitting on top of it.
Okay.
Now the angles, this is called tetrahedral, and all the angles are going to be 109.5. So this is how, let me also show you uh, a tetrahedral shape for carbon. We did this as well in hybridization. So this is how it actually, I mean, there was a, so this is how it actually looks. Okay, no matter how, whichever way you put it, it's going to look exactly the same. Okay, if you look at it from the side, this is the pyramid, the three-sided pyramid, and this is the bond that's sitting on top of the pyramid. Okay, so if you see it from the front, then this is your three-sided pyramid, and this is the bond.
Okay.
Okay, so no matter which way you rotate it, it has rotational symmetry. It's called rotational symmetry, which means no matter how you rotate it, it looks exactly the same. Uh, Now that's tetrahedral. That's four bonds. So whenever you see four bonds, it's going to be the same. So for example, a lot of molecules have four bonds. SO4 2 minus has a similar structure. It's one bond coming out of the page, one So this is a sulfate ion, SO4 2 minus. So a lot of molecules, remember, double bonds have to be considered as one thing. I said next one, B. The variant of this, that's one lone pair and three bonds.
Yeah.
Now, if you have one lone pair and three bonds, the shape is described as trigonal pyramidal. And the angle kind of shrinks to 107 degrees. Okay? So what happens when you have this shape? The shape would remain pretty much the same. Like if you have an NH3 molecule, it's going to be
Yeah.
exactly the same because in total there are four electron densities.
Okay.
So it looks exactly the same, except for the fact that in an NH3 molecule, on three sides it's hydrogen atoms, and on the fourth side the orbital is full, completely full. So that's a lone pair. Okay, so the top is missing. So think of the triangle pyramidal shape with the top gone because there's nothing attached. So it's like a pyramid now, a three-sided pyramid.
Okay.
And the reason the angle kind of shrinks is because I told you that lone pairs exert greater repulsion. So the lone pair sitting on top is
Okay.
going to be pushing the bonds closer to each other. As a part C.
Okay.
Part C is if you have two lone pairs
Mm-hmm.
and two bonds. So it's the same four electron densities, except now the shape is going to be bent, or you can call it nonlinear,
Okay.
and the angle would be even lesser. It's going to be 104.5. It's going to be 104.5 degrees. So you still have four electron densities. So look at water. So water is going to have one electron density on the top, one on the left, one coming towards you out of the page, the other one going into the page. Okay, so it's the same four electron densities as far away from each other as possible, except with water. You're going to have hydrogens bonded to two of them, and on two sides the orbitals are full. They're lone pairs.
Okay.
So they won't be counted in the shape. So the molecule is going to be this one. That's going to be bent. You start off at a hydrogen, go to oxygen, then hydrogen back again. So it's going to be bent. And the angle would be even lesser. It's now 104.5 because you started off with 109 degrees over here. With one lone pair, the bonds got closer together. With two lone pairs, the bonds now are even further closer together. Is this clear?
Yeah.
So then the next one is if you have five electron densities. So now with five, you don't really get a lot of questions with five electron densities, but you might. The first version is if you have five bonded pairs of electrons. Okay, that's the first version. Now, how does the molecule look like if you have five bonds? The molecule looks kind of like this. There's going to be phosphorus, which is bonded to Cl. There's a bond.
Yeah.
So this is fan shaped. Phosphorus bonded to three Cls, right?
Yeah.
I said, but phosphorus would be bonded to five Cls. Where would the other two bonds come or would be attached? One would be on top, the other one would be at the bottom.
Okay.
So it's like basically it's like a fan. You can think of it as a fan that's hanging from the roof. So this bond is
Okay.
this bond is on top of the fan, and there's going to be something hanging from the fan at the bottom as well. So this is how five bonded pairs of electrons remain as far away from each other as possible. Now this molecule has two angles. The way it's going to have two angles is that these angles over here, there would be 120 degrees between the fan. And the angles between the fan blades and the top and the bottom, that's going to be 90 degrees. ठीक है, is this clear, Aman? Aman, is this clear?
Yeah.
That's the next version of the same molecule. That's the next version, part B, is that if you have one lone pair
Yeah.
plus four bonded pairs of electrons, right?
Yeah.
So how would the molecule look like? Now, I said these, it's going to be the same shape, okay, because you have five electron densities, so it's exactly the same shape. It's going to be one bond. I mean, there's going to be a fan in the middle. And there's going to be a bond on top and a bond at the bottom. So if this atom is bonded to, I mean, there's going to be one lone pair on one side, and on the other sides, there would be four bonds with four different atoms, right?
Yeah.
So it's basically the same shape with one side missing because there's already, I mean, the orbital is full, so there's no atom attached to it. This is called a seesaw shape because if you look at this shape from the side, one second. Okay, so if you look at this shape from the side and you remove the top, it looks like a seesaw.
Yeah.
Is this clear? I mean, it looks like a stand and there's
Yeah.
two persons sitting on both sides. I
Yeah.
mean, this is basically the same shape. The third one, part C, of the same molecule, same version, is if you have two lone pairs plus three bonds. So how would the molecule look like if you have two lone pairs? Same shape. You have X, and there is and there are this one. That's the same shape. Now you have two lone pairs. So the lone pairs are over here. So two of the blades of the fan are lone pairs now. So there's nothing attached on that side. On the other side, you have three bonds.
Yeah.
So if you get rid of this side, it's like a T-shaped molecule. I mean, if I highlight, so it's basically this, and this. So it's a T-shaped molecule. And the angles are 90 degrees or almost 90 degrees. And the fourth version is that if you have three lone pairs, okay, so there's a fourth D version which is you have three lone pairs and two bonded pairs. Now in this case, the shape is going to look like. As in this case, what would the shape look like? Starting with the same shape. And you have now the bonds would be on top and at the bottom, and the remaining three places the fan would be lone pairs.
Okay.
So this is going to be linear. It's going to be straight. Like there's a bond on top and there's a bond at the bottom, and the middle part that's all lone pairs. And let me. ठीक है, Amal, is this clear?
Yeah.
So this one is linear and the angle is 180 degrees. ठीक है, so that's 5 electron densities. ठीक है, and I forgot to write the name of the first and the second one. This is called trigonal bipyramidal.
Okay.
And this one is called a seesaw shape. Now, next one, the last one probably. That's if you have the last one is if you have 6 electron densities or 6 pairs of electrons in any shape or size. If you have so if you have 6 electron densities around an atom, then that's very simple. You have x, y, and z axis like an SF6 molecule. So you would have uh, we can think of it as this is the x-axis, this over here is the y-axis, and then there's the z-axis on top and below.
Yeah.
Okay, so there's 6 sides, and there would be a fluorine atom attached to each one of the sides. This is the z-axis, and all the angles are going to be 90 degrees, and this is going to be called an octahedral shape.
Okay.
So this one is octahedral. So that's 6 electron densities, and even that, I mean, this is A. Okay, A is if you have, let me make some room. So A is when you have 6 bonds.
Yeah.
The other version could be that if you have one lone pair, that's version B. So version B would be if you have one lone pair plus 5 bonds. And so what's going to happen in this? In this, what would happen is that there's going to be X. There's Y attached over here on all sides. So there's Y attached and Y attached. And there's going to be an atom attached on this side, and on top there would be a lone pair. So the top is missing. I mean, this side over here is missing. So it's like this is called square pyramidal because if you connect all the dots, I mean this is x, y, and z axis. If you connect them together, it's going to be a square. And if you connect it with the bond that's on the z axis, then it looks like a pyramid. Okay, so it's like a pyramid with a square bottom. Okay, Amal, is this clear? And let me show you how a square pyramidal shape looks like.
Okay.
Okay, it's going to look like this. I mean, the one over here. Okay, the middle
Oh,
part.
okay.
I mean, there wouldn't be anything at the bottom. Okay, the bottom bond is missing. There's going to be a lone pair over there, but that side is missing. So this is like a pyramid with.
Oh, okay.
This is like a pyramid with a square base. Or there's going to be just one last version, which is for the same one. So it's A, B, and C. So the last one is uh, 2 lone pairs and 4 bonds. Now this would be simple that there's going to be X. There's going to be bonds on the y-axis, X and y-axis. And on top, and at the bottom there would be lone pairs. So on two of the sides where you had bonds previously, now you have lone pairs. So two of the sides are missing. So this is just square planar. It's going to be a flat planar molecule.
Okay.
Okay, so this is going to be a square planar
Yeah.
molecule. So these are all the shapes that you have to learn. You don't need to learn most of the 5 electron densities. I mean, this would be sufficient. Okay, they don't go into
Okay.
a lot of detail. Apart from these haven't really been asked a lot. Okay, so very few questions on this, but other shapes they're very very important. And remember that the shape is decided by the central atom. Like, I mean, look at the central atom in a molecule and figure out how many bonds does it have. So, so when you're trying to determine the shape, it's always the middle atom that's going to decide what the shape is. I mean, the shape of this
Okay.
molecule is not determined by the atoms that are on the outside.
Yeah.
So I'm going to, based on this, I'm going to give you a question. Try and tell me what the shape of each of the, what is the angle and so let me draw the molecule first. So this one. The first one is, look at this green carbon atom over here. Can you tell me what the angle is?
So,
I mean, you can use the board as well. Let me send you the board link.
okay.
1 second.
But would it be like a would it be a triangular plane around the first carbon atom because the three hydrogens?
Hey, how many bonds does it have?
Four.
Okay, so it has 4 bonds. How would 4 bonds in a three-dimensional shape remain as far away from each other as possible? Remember, a three-dimensional shape. Uh,
Yeah.
because so 4 bonds, go and look at 4 electron densities. And if you have 4 bonds, they're going to be,
Oh, so it's going to be a tetrahedral bond.
yeah, it's going to be tetrahedral and it's going to be 109.5 degrees. So this is how, and let me try and draw this. So it's going to be hydrogen. There's going to be a bond, or there's going to be one bond coming out of the page, one going into the page. So there would be 3 hydrogens, right?
Okay.
And on this side, there's going to be a carbon. Okay, so let's focus on this other carbon atom now, the second one. What do you think? I mean, where did the carbon go? What would this look like? How many electron densities does it have?
Um, it has three.
So it has 3 electron densities, right? There's a double bond, and I think
Yeah.
a double bond is one thing, right? So if you
Yeah.
go back and look at 3, and all of them are bonds, right? So
Yeah.
3 electron densities is fan shaped, right?
Yeah.
Whether they are double bonds, they would be fan shaped. I mean, if there had been a lone pair, then it would have been. How did you know that there was no lone pair in the molecule?
Because all of them are being like used up. There was none left because carbon has
4 electrons,
six.
right?
Yeah, carbon has four electrons that had to share, and then it was sharing them with. Then it was making like three bonds, and one of them was a double bond. So all of the
All of them
electrons
get
were.
used. They're getting used up, right? Yeah.
Yeah.
So, so this one is going to be fan shaped, right? So I mean, this is the carbon I'm trying to draw now. I mean, I've
Yeah.
drawn one side. This is the CH3 side. So that's tetrahedral. So this carbon is going to be the shape around this is going to be fan shaped, right? So
Yeah.
angle would be 120 degrees. So let me. So it's going to have a double bond with another carbon atom,
Yeah.
and at the bottom there's going to be n, right?
Yeah.
Acha, tell me what this n would. I mean, n never forms four bonds. I mean, I drew too many. I said, tell me what this n, what the shape around this n would look like.
Um, this would be a trigonal plane because it's making three bonds.
No, but does it have lone pairs? It's in group five.
Yeah.
So it's basically four electron entities, right? But
Yeah.
one of them is a lone pair. So where's four electron entities? This one. So it's one lone pair and three bonds. So
Yeah.
it's going to look like a pyramid. Okay, is this clear?
Yeah.
So let's I'm going to draw an inverted pyramid now because so it's going to look sorry. So it's going to look like a pyramid
Yeah.
because there's a lone pair sitting on top. Okay. I said this other carbon atom I think is exactly the same like this carbon atom. So that would be fan shaped as well, right?
Yeah.
So that's also fan shaped, and one side there is H, and then you reach this C triple bond N. So what would be the shape around this C? Triple bond
Uh,
and a single bond.
would that just be a linear one? Because
Yes.
yeah, it's only making
Okay, that's going to be linear. That's fine. So
yeah.
basically, this is how the three-dimensional shape of this molecule would actually look like. And I told you that I told you that rotation is not possible around a double bond. So which means these are stuck in position. I mean, you can't rotate this. You can't twist the molecule at this point.
Yeah.
Plus this tetrahedral shape over here, this would be spinning like a fan because this is a sigma bond, and I told you that rotation is possible around a sigma bond.
Yeah.
Like if you have these three, this pyramid over here would be rotating around. The same would be true for this one. I mean, this is a sigma bond, so these two bonds would be spinning around, like rotating around.
Yeah.
But the double bond over here would be stuck in position. I mean, this part and this part, you can't sort of twist it around. TK, is this clear?
Yeah.
So, TK, we're going to continue with this in the next class then, TK. Hopefully, tomorrow if you're available.
Yeah, that's fine. But I think on the next weekend, um, can we reschedule the lessons because I have to work next weekend.
You have to?
Like I have to work next weekend, not this one, but the next weekend.
No, okay, sure.
'Cause-
Just message me.
yeah. Okay.
And we can reschedule, TK.
Yeah. Okay. That's fine.
Okay, then. Take care.